Hello, I'm Don Wunsch, Mary K. Finley, Missouri Distinguished Professor of Computer Engineering at Missouri University of Science and Technology and Chair of the IEEE Computational Intelligence Society History Committee. And I'm here visiting Bernard Widrow at his home in Stanford, California. And he has kindly agreed to show us the Memistor Adaline.
Hello. Yeah. I guess you have to move your camera.
Yeah, I'm going to move it around so we can see.
This is the Adaline, which is a single neuron, and its synapses. So the input array, the input vector, is a 4x4, which we can represent as a pattern. And you can see in the lights we can make patterns so that we can control the input to this single neuron. Now, what I'll do is I'll do a problem that I've done many times, so I know how my fingers automatically know how to do it. Now, this input, let's say right here, this is +1, that's -1. So the inputs on this particular Adaline are binary, although in principle they could be analog. Any input level is okay. Now, you can see in the lights which way the switches go. So we made it binary so you can put in a pattern and you can see it in lights. Only one problem is the particular indicator light. This one here burned out. And since this machine was built probably around 1961, roughly in that time frame.
That's when I was born.
Before you were born, yeah.
About when I was born.
But certainly not before I was born. This particular light bulb doesn't work anymore, so that's a dead light, but everything else works fine. Except that
there's a lot of stuff in back here that's
some of the synapses, you can see them. I don't know if you can see it.
Yeah, we can see it.
They're right there.
Yeah.
So there's 17 of them. So it's got a bias weight and 16 weights.
So the bias weight's very important to make these things work.
Sometimes it's not. Mostly you don't bother with it, but it's okay. The Memistor, see if I look to see if I can find one. I had some on my desk, but I don't know where they are right now. I guess I can't find it.
Yeah. Okay.
No, we don't see it.
Okay.
The Memistor is a little cell that is sealed. It's full of a copper sulfate and sulfuric acid plating solutions, electroplating. You have a little resistor element inside this sealed glass cell, and the resistor is made out of noble metal, so that the resistor doesn't get dissolved in the acid. With the acid solution, there's a third electrode that has a source of copper. So you can electroplate copper down onto the resistor element. By doing that, with no plating on the copper element, it measures about 10 ohms. When you fully plate it with copper, it goes down to about 1 ohm. So it's about a 10-to-1 ratio. So we use that as a weight. And I'll show you exactly how it works. And actually what this is implementing is the least mean square, or LMS algorithm. I can put that up, yeah. Now with all the switches up, this is the adapt control. When I push that to the right, I'm plating every one of those weights. I'm increasing the weight. When I go this way, I'm decreasing the weight. And you can see, if you look at the meter, the reading of the meter, you can see this is an analog memory, and it's continuously variable. Actually, when you do it, what you're doing is you're laying down molecules of copper down on a resistor element. So it's just very smooth and continuous. there, to my knowledge, there is no analog device yet that can do what that does. And we made these at the beginning, I think it was around the end of 1959 when we made the first Memistors.
Wow.
And so now, if I have all the switches up, and I go to the right, I'm increasing all the weights. When I go to the left, I'm decreasing all the weights. If I take this particular input and put that down, now when I go to the right, I increase the weight of everybody except that one. That one decreases. If I go this way, they all decrease except that one increases. So whether the weight increases or decreases depends on whether the input is +1 or -1, and whether the error signal is positive or negative. So what we normally do is to train this neuron to give a binary output, although it could give you a continuous analog output. But with a binary output, halfway out on the right-hand side of the scale is we consider +1, and halfway down on the other side -1. So if we let's say I put them all up. Now I go that way. What I'm saying is the desired. Well, all right. Let's suppose for this particular set of inputs, I'd like the output response to be -1. So now the desired response is here. The actual response is here. The error is the difference between a minus something and this is a plus something. It gives you a negative error, and a negative error means you subtract the input vector from the weight vector, and by doing that you push this way and you hold it. Well, you can hold it till you get the result you want. If you want that to give you a +1 output, you do it like that. Now what I'll do is I'll put in a pattern. If I do it, I can remember what I put in. If I don't do a familiar pattern, I'll forget how to do it. So this is a T. Just happens that the response is 0. Now suppose that we'd like the response to the T pattern to be +1. So +1 is right about here. So what I'll do is go like that. Whoops. Well, it's okay.
Yeah.
I'll put in a J pattern. That's reading negative, and suppose I want that to be negative. Well, it already is. It's a little more negative than I want, so I can reduce it a little. I can just put it right where I want. Now, suppose that we put in shifted T, shifted by 1 pixel to the right. That's a completely different pattern.
Yeah.
It doesn't know the difference. So I'd like the T to give a plus response, and it's giving a minus response. So let's fix that. Whoop. There you are. Good. Now let's put in a J pattern. And remember that this light is not working, but this one is. So now I've got in the J. I want that to be minus. So I put it right there. So now we go back, put in a T, and that's plus. I'll leave it alone. It's okay. I can if I want, play with it to get it just right. That's a J.
A little bit minus.
That's been hurt because you see the shifted T
has a big overlap with it.
Yeah, shifted T has a lot in common with the original J, and so now we can make that a little more negative. There's the J. Here's the T. Make that a little more positive. There's the J, and that's -1. So let's see what the original T looks like. So every time you put in something new, you train it, you adapt, and you tend to screw up a little bit stuff you've already got in there. If you keep doing it over and over again, eventually it'll sink in. And what the LMS algorithm is a algorithm I call a minimal disturbance algorithm.
Don't rock the boat.
Every time you train it, you're training it in such a way that you're training it to give you the result you want, but do minimal disturbance to patterns that are already in there. So that's a property of the LMS algorithm. The perceptron rule is the same thing. It also is a minimum disturbance algorithm. Backprop is a minimum disturbance algorithm. These are all gradient algorithms. Okay, so now let's suppose I put in a T pattern. Well, let's say I put in a big X pattern. Big X. Let's say I wanted that to be plus. It already is, so we're lucky. Half the time you're lucky, so you can put it like that. So let me put in a big T pattern. Big T pattern looks like this. That's a big T. So we want that XT. Let's say we want that T to be minus. And we put in a big C pattern. Make that plus. And put in a big J pattern. Yeah, that's a big J pattern, and make that minus. So by doing all that adapting, we're screwing up our original. But let's see how the big X goes. Whoops. Let's see, I want that. I want these like that, and that's up. Yeah, so that's a big, whoops, big X pattern. Yeah. That's supposed to be plus. And we put in a big T pattern. Big T pattern, that's minus XTCJ. Let's put in a C pattern. Big C. Now I'll do it like this. And make that plus, and that's okay. Put in a big J pattern. Yeah, that's a big J pattern. We want that minus, so that's okay. So let's check it again. Put in a big X. That's plus. Put in a big T. Yeah, everything's good. T is minus. Put in a C pattern. C is plus. And big J is minus. So we got the XTCJ. Now let's see what damage we did to our original patterns. Little t is plus. It's reading 0. So it's not terrible, but it's not right. There's J, and that's a little bit negative. Here's the T, that's reading about 0. And that's J, and that's supposed to be minus, and that's fine. Leave it alone. Well, let's go back to the T. Make that guy plus. Whoop. And make this J. Make that minus. T plus J minus. So that's good. Let's put back the T, little t, plus J. It's minus, it's okay. T is plus. J is minus. So those are okay. Now what do? We probably screwed up some of the big guys. So this is an X. That's plus, that's good. T is reading 0. It should be minus. And put in the big C. It's supposed to be plus. It's plus. And big J is supposed to be minus. It's minus. We practically got these right. Let's see. The big X. Oops. Big X.
This one needs to be.
Oh, that makes a difference, doesn't it?
Yeah.
Okay, so the X, the big X is correct, and the big T. Let's see what that looks like. It's supposed to be minus, and it is. The big C is supposed to be plus, and J is supposed to be minus. It is. So we got them all in.
Good. By the way, I notice you have a plaque with the equations right behind Rona's picture there.
Yeah.
Yeah.
There's a book that goes in there. I got it upstairs. I'm using it. That's my
Great.
Widrow Stearns book.
Yep.
But I was going to tell you something about this machine. A few of the Memistors in it are not working.
And it works anyway.
Works fine.
Yeah. That's robust.
That's right.
Yep.
What they call this algorithm bulletproof.
Mm-hmm.
And this is this LMS algorithm is the basic algorithm of essentially all adaptive filters.
It's in every modem, every noise cancellation node.
Every modem in the world uses that algorithm.
Every echo cancellation system.
I had a meeting right here. I demonstrated this to a nice gentleman who is in charge of the signal processing group at Apple.
Mm-hmm.
And he told me that every iPhone that they shipped since the iPhone 5 has got LMS algorithm in it all over the place. And he said that if they told me how they're using LMS algorithm in the iPhone, they'd have to shoot me before they let me out of the place. I went to Apple. I went to one infinity circle to go to the, in other words, the mother church.
I'm glad they didn't tell you.
Well, I went there to meet the whole signal processing group. They all wanted to touch me. They say, "You're alive. You're real."
Yeah.
And they wanted me to tell them the story about the discovery of the LMS algorithm. And so I told them, and they were very pleased. And that's where they told me that if they told me how they're using it in the iPhone, they'd have to shoot me before they let me out.
Well, I'm very pleased that you've taken the time to tell us too, so thank you, Bernie.
It's a pleasure.
Yep, and thanks for having me to your home and getting to see your machines and all the wonderful art you've collected as well. So, okay, so we'll sign